the sound of a subtle, deep hum, like a cosmic resonance. We live in a universe that appears chaotic. Galaxies collide, stars explode, and particles flicker in and out of existence. But beneath this cosmic turbulence lies something extraordinary, an underlying order. Everything we see, from the smallest atom to the grandest galaxy cluster, follows invisible rules. There are patterns that repeat, symmetries that hold, and numbers that never, ever lie. The universe somehow looks mathematical. But why? Why should existence itself obey equations? Why should nature's laws be written in the language of symmetry? It's a question that has baffled scientists and philosophers for centuries. Think about it. From the delicate six-fold symmetry of a snowflake to the spiraling arms of a galaxy, from the precise orbits of planets to the perfect structure of a crystal, every level of reality seems to hum with a hidden balance. This isn't just a coincidence. It's a fundamental clue about the nature of everything. In today's video, we're going to explore this profound mystery. We'll investigate how symmetry shapes the very laws of physics, gives rise to matter, and might even point to deeper hidden dimensions of reality we can't yet see. This is a journey into the heart of creation. Have you ever wondered where all the different particles in the universe came from? It turns out, the answer lies in a concept called broken symmetry. We'll uncover how the early universe, in its first moments, was a state of perfect, unimaginable symmetry. But then, it shattered. This cosmic cataclysm wasn't an accident. It was the event that created the rich diversity of forces and particles that make up our world today. And at the center of this story is a celebrity of the particle world, the Higgs boson. This tiny particle is the key that revealed how nature chooses which symmetries to keep and which ones to break, ultimately giving mass to the universe. We'll follow a mind-bending mathematical trail that connects things that seem completely unrelated crystals on Earth, abstract equations on a blackboard, and the colossal dance of galaxies across space-time. It's a detective story on a cosmic scale where the clues are written in the language of mathematics. And as we piece them together, we'll confront the ultimate question: could perfect symmetry be the master key, the theory of everything that explains it all? Join us as we dive deep into the story of how the universe learned mathematics and why it never forgot. This is the story of the hidden symmetry that governs our reality. In the very first moments after the Big Bang, our universe wasn't made of things. It was made of symmetry. Picture a blinding sea of energy, where every particle that exists today, electrons, quarks, photons, was part of a perfectly balanced, unified state. Physicists call this the symmetric phase. All the fundamental forces of nature, gravity, electromagnetism, the nuclear forces, were one and the same. Their laws were interchangeable. In a way, it was a universe without a distinct identity. But symmetry holds a paradox. It's both beautiful and incredibly fragile. As the universe expanded and cooled, these perfect symmetries began to fracture. The forces separated, particles diversified. The unified field split apart into the complex physics we know today. This process is called symmetry breaking, and it's one of the most profound and creative events in the entire history of the cosmos. To really get our heads around how the universe broke its own perfect symmetry, we first need to understand what symmetry even means in physics. In our everyday lives, it's pretty simple, right? Butterfly's wings mirror each other, snowflake repeats its pattern in 6 directions. But in physics, symmetry is something much deeper. It means invariance. Think about it. If you rotate a perfect circle, it looks exactly the same. If you take a law of physics, like gravity, and test it here, and then test it on the other side of the galaxy, it still holds true. That invariance, the idea that nature as rules don't change when you transform them in some way, that is symmetry. Mathematically, symmetries are described by special sets of transformations called groups, which leave a system unchanged. And here's the mind-blowing part. Every fundamental force in nature is rooted in one of these symmetry groups. Electromagnetism follows a symmetry called U1. The weak nuclear force is governed by SU2. The strong nuclear force by SU3. Together, they form the elegant mathematical architecture of the standard model of particle physics, our best description of the universe. Fundamental building blocks. The crucial link between symmetry and the laws of physics was discovered by a true titan of science, the mathematical genius, Emmy Noether. Back in 1915, while Einstein was finalizing general relativity, Noether proved one of the most elegant and powerful theorems in all of science. It's known simply as Noether's theorem, and it states that for every continuous symmetry in nature, there is a corresponding conservation law. It's a beautiful, direct connection. If the laws of physics don't change over time, that's time translation symmetry, then energy must be conserved. If the laws don't change from place to place, that's spatial translation symmetry, then momentum must be conserved. If the laws do unchanged no matter how you rotate your experiment rotational symmetry, then angular momentum must be conserved. Noether's theorem revealed that symmetry isn't just about aesthetics. It's the very foundation of order. It's what makes the universe coherent and predictable. Without it, the cosmos would be pure chaos, a place where the rules of reality could change from one moment to the next. So let's go back to that perfect beginning. In the first trillionth of a second after the Big Bang, the temperature of the universe was so unimaginably high that all particles and forces were merged into a single, seamless whole. Physicists call this the Grand Unified Epoch. During this time, the universe might have been described by a single, unbroken symmetry, a kind of superforce. But as space expanded, it cooled. This cooling acted like a cosmic phase transition, similar to how water vapor condenses into liquid and then freezes into solid ice. And with that cooling, the first great symmetry broke. The strong nuclear force split away from the unified field, becoming its own distinct entity. A little later, as the universe cooled further, the electroweak force divided into electromagnetism and the weak nuclear force. Each one of these breaks shattered a piece of the universe's initial perfection, but in doing so, created the distinct particles and forces that make our world possible. In this sense, everything you see around you, from the atoms in your body to the distant galaxies, is a fossil of broken symmetry. And here we arrive at the central paradox of creation. For anything to exist, perfection had to give way to imperfection. The universe began in a state of flawless balance. Yet that very balance had to be broken for matter, for diversity, for complexity to emerge. Imagine balancing a pencil perfectly on its sharp tip. It's a state of perfect symmetry. But it's unstable. Eventually it will fall. When it falls, it has to choose one direction out of an infinite number of possibilities. And in doing so, it breaks the symmetry. The early universe did the exact same thing on a cosmic scale. Its fall from that state of perfect symmetry is what gave rise to everything that exists. The broken pieces of that initial perfection became the building blocks of reality. And even though that original balance was shattered, the patterns of symmetry remain, hidden deep within the laws of physics, whispering to us through mathematical equations and encoded into the very geometry of space-time itself. Today, modern physics recognizes that symmetry isn't just a convenient feature of our universe. It is the blueprint of nature itself. The very structure of an electron's field, the specific energy levels of atoms, even the stability of matter, it all depends on the deep underlying symmetries of quantum fields. It's everywhere you look. When you see a crystal, you're observing atoms arranged in a repeating symmetric pattern. When you hear a musical octave, you're sensing a kind of symmetry in frequency and ratio. When you observe the graceful orbits of planets or the spiral arms of galaxies, the same fundamental symmetries appear again and again, scaled across unimaginable distances. It's as if the universe is humming a hidden rhythm, a deep mathematical music that governs all of reality. And physics is our attempt to learn how to play it. I thank you so much for joining me on this journey through the cosmos. If you enjoyed this exploration of symmetry, don't forget to like, subscribe, and hit that notification bell for more deep dives into the universe's greatest mysteries. See you next time. If the early universe began in perfect symmetry, something had to decide when that perfection would end. Something wasn't a god but a field. An invisible ocean that fills every corner of space, the Higgs field. For most of human history, empty space was just that nothingness, a vacuum. But in modern physics, we know even the void is alive with energy fields. Among them, one is unique. It doesn't carry light or bind atoms together. Instead, it gives mass, the very property that makes matter, matter. This is the Higgs field. When the universe was brand new and searingly hot, This field was perfectly balanced at zero. But as the cosmos cooled, the field settled into a lower energy state, like a ball rolling into the bottom of a valley. This shattered the universe's perfect symmetry. Particles that once zipped around at the speed of light suddenly found themselves interacting with this new field. The more they interacted, the heavier they became. This was the birth of mass. Imagine a grand cosmic dance floor. In the beginning, all particles moved in perfect weightless harmony. Then, the Higgs field switched on, filling the floor with an invisible, molasses-like substance. Some particles, like photons of light, slipped right through, unaffected, continuing at light speed. But others, like the W and Z bosons, had to wade through it. They were slowed down, gaining inertia. That resistance, that stickiness, is what we experience as mass. It's why stars have weight, planets have gravity, and matter can clump together to form galaxies, planets, and you. Without the Higgs field, the universe would be a ghostly sea of pure energy with no structure at all. For decades, physicists suspected this field existed, but how do you detect something that's everywhere and nowhere at once? The answer was to look for a ripple in the field itself, a particle known as the Higgs boson. Think of it like a wave traveling through water. The field is the water and the boson is the wave. In 2012, at the Large Hadron Collider deep beneath the border of France and Switzerland, one of humanity's greatest scientific quests reached its climax. Scientists smashed protons together at nearly the speed of light, recreating the extreme energies of the universe just a trillionth of a second after the Big Bang. And in that fleeting, chaotic moment, the Higgs boson appeared. Its discovery was monumental. It didn't just confirm the existence of the Higgs field. It validated the entire standard model of particle physics. It was the final, missing piece of the puzzle, the key that proved our understanding of the universe's fundamental symmetries was correct, and that their breaking is the very reason we exist. What makes the Higgs so profound isn't just that it gives mass. It demonstrates a fundamental cosmic principle. Symmetry breaking is an act of creation. When the Higgs field chose a specific value instead of remaining at zero, it selected one version of reality out of countless possibilities. This choice made the universe asymmetrical, yet infinitely more complex and structured. It's as if the universe, to become interesting, had to pick a side. This principle repeats itself everywhere. In the early universe, symmetry breaking separated the fundamental forces of nature. In biology, it's what tells an embryo how to develop a left and a right side. In materials science, it's responsible for creating crystals, magnets, and superconductors. Far from being a flaw, symmetry breaking is nature's engine for generating diversity. From a state of uniform perfection, all the complexity we see around us was born. When physicists write down the equations that govern the universe, they often strive for a kind of artistic elegance: clean, balanced, beautiful. This isn't just a matter of taste. Nature itself seems to favor mathematical beauty. The great physicist Paul Dirac once said, "It is more important to have beauty in 1s equations than to have them fit experiment." This very intuition led him to predict the existence of antimatter decades before it was ever observed. Symmetry was his guide. Modern physicists follow the same principle. Standard model wasn't built through trial and error. It was deduced from the elegant logic of symmetry. Every particle, every force, every law of conservation can be traced back to an underlying mathematical symmetry. But this beautiful model has its limits. There are hints of even deeper symmetries, like supersymmetry, which suggest that every particle we know has a hidden partner. So far, these partners remain undiscovered. Perhaps like the Higgs boson before them, they're just waiting for us to build the next great machine. The next powerful instrument capable of peeling back one more layer of reality. There's a beautiful irony in all of this. Symmetry often hides itself by breaking. Every time a symmetry is lost, something new is gained to form: a mass, a pattern, or a law. What appears to be an imperfection is actually the universe revealing its hidden structure. The discovery of the Higgs boson showed us that even apparent chaos is governed by order, that beneath the randomness lies a deep mathematical necessity. When we study the equations that describe these fundamental interactions, we're not just inventing abstract human concepts. We are discovering the very geometry of existence. Symmetry, it turns out, isn't just about what looks good. It's about truth. a truth so profound that it shapes our reality at every conceivable level. But the Higgs wasn't the end of the story. It was the beginning of a much deeper mystery. If symmetry defines the universe, and breaking it gives it form, what lies beneath even that? Are there hidden dimensions where all forces and particles are united once more in a perfect, unbroken symmetry? For all its power, the standard model of particle physics isn't the final word. It's more like a beautiful mosaic, perfect in its design, but missing several crucial tiles. It describes how the universe behaves, but not why its laws exist in the first place. Why do particles have the masses they do? Why are there exactly 4 fundamental forces? Why does the universe favor matter over antimatter? To answer these questions, physicists began searching for deeper symmetries, ones that might lie hidden beneath the familiar fabric of reality. What they found led to some of the most astonishing and controversial ideas in modern science: supersymmetry, extra dimensions, and the possibility that our universe is only one pattern in a much larger mathematical tapestry. The standard model is remarkably successful. It predicts the outcomes of particle collisions with stunning precision, yet it leaves several huge mysteries unresolved. For one, it cannot explain gravity. It says nothing about dark matter or dark energy, which together make up 95% of the entire universe. And it gives no reason why the Higgs field has the exact strength it does, a puzzle known as the fine-tuning problem. Physicists suspect that these missing pieces aren't just accidents, they're clues. They're signs of a hidden symmetry that the standard model only partially reveals. The universe, it seems, may be governed by a deeper order, one that unites particles we know with those we have not yet seen. Enter supersymmetry, often abbreviated as SUSY. It's one of the boldest ideas in theoretical physics, proposing that every particle we know has a secret twin. Each matter particle, like an electron or a quark, has a force-carrying partner, boson. And each force particle, like a photon or a gluon, has a matter-like counterpart, a fermion. In this picture, nature elegantly balances its own equations. If true, supersymmetry would literally double the known particle zoo, predicting entities with names like selectrons, neutrinos, and gluinos. But this isn't just a mathematical curiosity. Supersymmetry solves some of the universe's biggest puzzles. It stabilizes the Higgs field, preventing our universe from collapsing under its own quantum fluctuations. It also offers a natural candidate for dark matter, a stable supersymmetric particle called the neutralino, which could be drifting through us at this very moment. And it hints that at higher energies, all of nature's forces might reunite under a single, symmetrical framework, restoring the unity of the early cosmos. In essence, supersymmetry proposes that balance isn't broken, it's just hidden from our view. At the Large Hadron Collider, scientists have been hunting for signs of these supersymmetric particles for over a decade. So far, none have appeared. Now, this doesn't mean supersymmetry is wrong, it just means that its hidden partners might be much heavier than we can currently detect. Some theorists suggest the next generation of colliders, which will be 10 times more powerful than the LHC, might finally reach the energy threshold where these hidden symmetries become visible. Others believe we may have to look elsewhere in the subtle ripples of cosmic radiation, in the large-scale patterns of dark matter distribution, or even in the quantum fluctuations of space itself. Either way, the pursuit of supersymmetry has reshaped how physicists think about the universe. It's not just about finding new particles anymore. It's about understanding why our universe seems so perfectly balanced on a knife's edge, tuned for complexity, yet never perfectly symmetric. Beyond supersymmetry lies an even more ambitious idea: string theory. At its heart is a radical proposition that the universe's most fundamental ingredients are on point like particles, but tiny vibrating strings of energy. Each unique vibration of a string corresponds to a particle's identity's mass, its charge, its spin, s, as if all the particles in the universe are just different notes played on the same cosmic instrument. But for string theory to work mathematically, it requires something extraordinary: extra dimensions. It's not just 3 dimensions of space and 1 of time, but as many as 10 or 11 dimensions in total. These hidden dimensions aren't somewhere else. They're curled up within every single point in space, incredibly tiny and invisible, like the intricate loops of a microscopic origami. The symmetries of these higher dimensions could finally explain why our universe's forces appear so distinct. What we perceive as separate interactions, gravity, electromagnetism. The nuclear forces may just be shadows of a single unified law, projected from a higher dimensional symmetry. It's a breathtaking vision. The entire cosmos as a multi-dimensional symphony of geometry and vibration. One of the most stunning discoveries in modern theoretical physics is the concept of duality, the idea that two completely different physical theories can actually be describing the exact same reality. For example, a theory with strong, complex interactions might have a mirror image a dual that is weak and simple. A theory defined in a higher dimensional space might perfectly mirror a different theory in fewer dimensions. This principle reached its most elegant form in the ADS-CFT correspondence. Proposed by Juan Mendocino in 1997, it suggests that a universe with gravity, like ours, might be mathematically equivalent to a lower dimensional universe without gravity, a holographic dual. In other words, our entire three-dimensional world could be a kind of hologram. Wow. Projected from a flat, two-dimensional boundary far away. This is symmetry on a cosmic scale, not a symmetry of shapes or fields, but of entire realities themselves. The universe, it seems, might be a grand hall of mirrors, where every law has a reflection. The deeper physicists go, the more the universe appears not just asterisk described asterisk by mathematics, but asterisk made asterisk of mathematics. This idea, championed by cosmologist Max Tegmark, is known as the mathematical universe hypothesis. It proposes that our physical world is, in fact, a mathematical structure. Existence itself is a form of geometry, logic, and number. In this view, symmetry isn't just a property of nature, it is nature. Every physical phenomenon, from the pull of gravity to the behavior of quantum fields, is simply an expression of an underlying mathematical consistency. If this is true, it would mean that the universe didn't just adopt mathematics as its language. The universe asterisk is asterisk mathematics, a self-consistent system of relations that is capable of generating awareness through beings like us, who can then ponder the system we are part of. But even as these ideas grow more elegant, they also become harder to test. Supersymmetry remains unconfirmed. Extra dimensions, if they exist, are curled up far beyond our technological reach. And the holographic principle, though mathematically sound, is still waiting for direct experimental evidence. Still, there is something deeply compelling about how these theories all converge on the same core idea, that beneath the apparent chaos of the universe lies a deeper hidden symmetry, one that may unite everything from the smallest quantum particle to the curvature of space-time itself. Each discovery seems to peel back one more layer of the cosmic code, only to reveal that the pattern continues deeper, more intricate, and more symmetrical than we ever imagined. Perhaps the final truth isn't a single equation, but an infinite symmetry one that never truly ends. Have you ever looked at a spiraling shell, a honeycomb, or the intricate pattern of a snowflake and felt a sense of wonder? It's not just beauty you're seeing, it's a language. Symmetry isn't just a cosmic principle, it's the language through which humanity learned to read the universe. Long before powerful telescopes or quantum computers, ancient civilizations saw these patterns all around them. They realized that the cycles of the sun and moon, the growth of plants, and the shapes of crystals weren't random, they were mathematical. And this realization built a bridge, a way for our minds to connect with the cosmos, to turn thought into a tangible understanding of reality. Look closely at nature. A sunflower's seeds arrange themselves in a perfect spiral following the Fibonacci sequence, maximizing space. Snowflakes always grow with six-fold symmetry, a direct result of how water molecules bond. And crystals form lattice structures that repeat endlessly, revealing symmetry on an atomic scale. Humans, instinctively drawn to these patterns, mirrored them in our own creations. The Parthenon in Athens and the great cathedrals of the Renaissance were built using the golden ratio, a mathematical proportion found throughout the natural world. Indigenous cultures aligned their sacred sites with solstices and equinoxes, reflecting a deep understanding of cosmic cycles. Even music is a manifestation of symmetry. Octaves, harmonics, and scales are all based on mathematical ratios. This profound connection suggests something incredible. The universe is intelligible because it's ordered. We can comprehend it because our brains are naturally tuned to its patterns. The journey from simply observing these patterns to truly understanding them began with the rise of formal mathematics. Think of the ancient Greek thinkers, like Pythagoras and Euclid. They weren't just doing sums, they were trying to decode the universe through geometry. Pythagoras famously declared that all is number, a revolutionary idea that connected everything from musical harmony to the motion of the planets. Euclid's book *Elements* laid down the geometric principles that would become the foundation of scientific thought for thousands of years. What they were beginning to uncover was one of modern science's most astonishing truths. The universe itself obeys these same mathematical structures. Flash forward to the scientific revolution, and mathematics transformed from a descriptive tool into the very language of physical law. Isaac Newton used his newly invented calculus to describe the laws of motion and gravity, revealing a hidden symmetry between forces and movement. A couple of centuries later, James Clerk Maxwell unified electricity and magnetism with a set of elegant equations that, astonishingly, predicted the existence of light as an electromagnetic wave. Then came Albert Einstein, who showed that the very geometry of space-time symmetry on the grandest scale governs the behavior of matter and energy. These breakthroughs prove a profound symmetry. The laws of nature are accessible to our minds because they are written in a mathematical language we can speak. Even today, our most abstract and complex theories, like quantum mechanics or string theory, are all expressed as precise equations. They are mirrors, reflecting the universe's deepest truths back to us. And this isn't just theoretical. Mathematics and symmetry physically shape the world we live in. The satellites that give us GPS navigate using the laws of orbital mechanics, a direct application of Newtonian symmetry. The crystals and semiconductors in your phone and computer, whose perfect lattice structures are products of geometric symmetry, form the backbone of our digital age. And massive machines, like the Large Hadron Collider, manipulate fields with incredible precision to uncover particles that existed only fractions of a second. After the Big Bang, through technology, we extend our senses, detecting the subtle symmetries that govern everything from the tiniest particles to the expansion of the universe itself. Our entire civilization, in a way, is a symphony of applied symmetry, a grand experiment to decode the cosmos. But why can we even perceive these patterns? Turns out our brains are hardwired for it. Neuroscience shows that we are built to detect symmetry, signal stability, predictability, and balance, all traits crucial for survival. Even as infants, we recognize symmetrical faces more easily. This is a fundamental biological instinct. But humans took this predisposition and elevated it into an intellectual art form: mathematics. Through numbers, geometry, and logic, we built a cognitive bridge from our minds to the underlying order of the universe. It's because of this bridge that we can study atomic structures, predict the orbits of planets, and even speculate about the shape of hidden dimensions. In a sense, humans have become the universe's mirror, reflecting its hidden patterns back upon itself. This deep appreciation for symmetry has also shaped our culture and philosophy. Renaissance painters like Leonardo da Vinci masterfully embedded the golden ratio and principles of perspective into their art, creating a beauty that feels both natural and divine. Philosophers, from Plato to Leibniz, have long wondered if mathematics was the key to understanding a divine order, even today. Architects and designers use symmetry to create spaces and products that feel inherently right and universally appealing. Across every culture and every era, symmetry has served as a bridge connecting observation, reason, and creativity, a powerful testament to the universe's deep mathematical logic. Ultimately, the story of symmetry is a story of human curiosity. We evolved on a small rocky planet, orbiting an ordinary star in a vast cosmos. Yet, we are capable of understanding the forces that sculpt galaxies, the lattice that build crystals, and the fundamental particles born in the explosive first moments of time. This is remarkable. It suggests that the universe wasn't designed in human terms, but in the universal language of mathematics, a language that we, through pure reason, can access and understand. Mathematics is more than just a tool. It is our cosmic translator. It allows stardust to understand itself, atoms to ponder galaxies, and conscious minds to catch a glimpse of the infinite. But how did we get here? How did we move from simply admiring a sunset to writing down the equations that govern the stars? That journey of discovery, from ancient speculation to the rigorous principles of modern physics, is a story for another time. Have you ever wondered what connects the graceful arc of a thrown ball, the intricate patterns of a snowflake, and the fundamental forces that hold the universe together? The answer is a single, profound idea: symmetry. This isn't just about pretty patterns. It's the secret language of the cosmos, a guiding principle that has led humanity on a centuries-long quest to understand reality itself. From ancient philosophers to the colossal particle accelerators of today, the story of symmetry is the story of our greatest intellectual adventure. It's a journey that reveals how the universe, as staggering complexity, emerges from a foundation of breathtaking simplicity and elegance. Join us as we uncover the hidden order that governs everything. Our fascination with symmetry didn't begin in a modern lab. It started with the ancients. Think of Pythagoras and his followers, who discovered that the pleasing harmonies of music were rooted in simple numerical ratios. They realized that nature, at least in sound, obeyed a hidden mathematical law. Plato took this further, imagining that the very elements of the world, air, fire, and water, were constructed from perfect geometric shapes, the Platonic solids. Centuries later, Johannes Kepler, gazing at the heavens, tried to fit the orbits of the planets within these same nested solids. While his model wasn't quite right, his instinct was revolutionary. He was searching for a geometric, symmetrical explanation for the motions of the cosmos. These early thinkers weren't doing physics as we know it, but they were planting a powerful seed. The belief that the universe is not random, but is governed by principles of order and beauty that we can describe with mathematics. The scientific revolution ignited this idea, turning philosophical musings into hard science. Isaac Newton's laws of motion and universal gravitation were a monumental leap. Suddenly, the same set of equations described an apple falling from a tree and the moon orbiting the Earth. The laws were universal. Hidden within Newton's work was a profound symmetry. The laws of physics do and change whether you re in London or Tokyo, whether you're facing north or south, or whether you perform an experiment today or tomorrow. This invariance under shifts in space and time is the very essence of physical symmetry, a concept later brilliantly formalized by Emily Du-Chatlet's work on energy conservation. The universe had rules, and those rules were the same everywhere and for all time. As we entered the 19th century, two forces of nature, electricity and magnetism, seemed like completely separate phenomena. That is, until James Clerk Maxwell unified them with four astonishingly elegant equations. His theory revealed that light itself was an electromagnetic wave, and that these fields possessed deep symmetries. The laws governing them remained the same, no matter how you rotated your perspective or moved at a constant speed. But the truly radical leap came with the quantum revolution. The bizarre world of the very small turned out to be governed by symmetry in the most fundamental way. Werner Heisenberg and Erwin Schrödinger developed new mathematical frameworks where the behavior of electrons and atoms was dictated by the symmetry of their wave functions. Then Paul Dirac, in a stunning display of creative genius, combined quantum mechanics with Einstein's special relativity. Driven by the pursuit of mathematical beauty and symmetry, his equations didn't just describe the electron. They predicted the existence of its mirror image twin, a particle of antimatter, before anyone had ever seen it. Symmetry was no longer just a useful guide. It was the core logic of reality. This led to the crowning achievement of 20th century physics, the Standard Model. This is our current best theory of nearly all the particles and forces in the universe. At its heart is a powerful idea called gauge symmetry. Think of it as a principle of ultimate democracy for physical laws. You can make certain changes to the underlying fields, and the physics you observe remains completely unchanged. Pioneers like Chun-Ning Yang and Robert Mills used this idea to describe the incredibly strong force that binds atomic nuclei together. Later, Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that electromagnetism and the weak nuclear force responsible for radioactive decay were actually two faces of the same coin, unified by a shared gauge symmetry. Every particle, every force, and every conserved quantity, like charge or energy, could be traced back to a specific symmetry. And this wasn't just abstract math. It made predictions. The theory demanded the existence of new particles, the W and Z bosons, which were discovered at CERN in 1983, a perfect confirmation. And in 2012, the discovery of the Higgs boson validated the final piece of the puzzle, the mechanism itself, based on a broken symmetry that gives particles their mass. Today, the quest continues at the frontiers of science. At the Large Hadron Collider, we smash particles together at nearly the speed of light, recreating the conditions of the early universe to probe symmetries at the highest energies. In condensed matter labs, physicists discover emergent symmetries in incredible new materials like superconductors and quantum magnets. And cosmologists look to the largest scales, finding symmetry in the faint afterglow of the Big Bang and the vast cosmic web of galaxies. Scientists are also chasing even more speculative ideas. Could there be a supersymmetry that partners every known particle with a heavier, undiscovered twin? Are there hidden extra dimensions of space whose symmetrical shapes dictate the laws of our own? Is our entire universe a kind of hologram projected from a simpler, lower-dimensional reality with deeper symmetries? Each experiment is a new chapter in this epic story. Of course, this is also a profoundly human story. It's the story of Emmy Noether, a brilliant mathematician who fled Nazi Germany and proved the fundamental theorem that rigorously links every symmetry to a conserved quantity. It's the story of Paul Dirac, who trusted the beauty of his equations to reveal a new form of matter. It's the story of visionaries like Murray Gell-Mann, who saw the symmetrical patterns that organized the chaotic zoo of subatomic particles into the simple family of quarks. These individuals and countless others show us that we can grasp the universe's deepest secrets, not with brute force, but through imagination, intuition, and the elegant language of mathematics. So, what has symmetry truly given us? It's more than just a pattern. It's a powerful predictive tool, allowing us to guess what we'll find before we even look. It's a design principle, explaining why the universe is built the way it is. And it's a philosophical lens, revealing that from a few simple, symmetrical rules, all the richness and complexity of the cosmos can arise. Every new discovery seems to confirm that symmetry is the golden thread connecting our human minds to cosmic reality. But the story isn't over. Dark matter, dark energy, the nature of gravity, these great mysteries hint at symmetries we have yet to find. The quest continues, driven by the belief that an even grander, more unified mathematical structure lies waiting to be discovered. From the graceful spin of galaxies to the elegant dance of particles within an atom, a single powerful concept governs the universe: symmetry. We see it in the architecture of life, in the double helix of our DNA, and in the very equations we use to describe reality. But for all we've discovered, the ultimate symmetry, the one that could unite every force, every particle, and every law of nature, remains just beyond our grasp. Could such a perfect order exist? And if it did, what would it reveal about the very fabric of reality? For decades, physicists have been on a quest for a theory of everything. This holy grail of science would finally bridge the gap between the colossal world of gravity, described by general relativity, and the bizarre, tiny realm of quantum mechanics. It's a theory that could explain why the universe seems so perfectly tuned for life, and perhaps even solve the mysteries of dark matter and dark energy, the invisible titans that dominate our cosmos. At the heart of this epic search is the idea of a grand unifying symmetry. Theories suggest that in the unimaginable heat of the Big Bang, all the forces we see today, gravity, electromagnetism, and the nuclear forces, were once one. String theory takes this even further, proposing that the universe's true symmetries are hidden away in extra dimensions, perhaps 10 or 11 of them. In this vision, our reality is just one expression of a higher dimensional harmony, a single thread in a vast cosmic tapestry. Where could these extra dimensions be hiding? The idea sounds like science fiction, but it could be the key. In a universe with more dimensions, forces that seem wildly different to us could simply be different facets of the same underlying entity. Think about it. Gravity's surprising weakness compared to other forces might just be an illusion, caused by it leaking into these hidden spaces. The properties of every particle, from its mass to its charge, could be determined by the unique geometry of these unseen dimensions. Detecting them is one of the greatest challenges in modern physics, pushing us to build ever more powerful colliders and incredibly precise detectors for gravitational waves. What if our entire universe is just a shadow, a projection of a much grander, higher-dimensional reality? The truth may be stranger and more beautiful than we can imagine. And this cosmic symmetry isn't just about physics. It echoes through biology and even consciousness itself. The elegant spiral of DNA is a masterpiece of helical symmetry, encoding the blueprint for all life. Inside our own brains, neural networks are built with repeating patterns, optimized for processing information. Even our sense of beauty is drawn to balance, proportion, and harmony. This raises a profound question. Is the emergence of consciousness itself just another expression of the universe's deep, mathematical order? Some thinkers believe that the laws that allow for life and intelligence aren't a lucky accident, but a natural consequence of a universe built on a foundation of symmetry. In this view, we are not just passive observers of this cosmic order. We are a part of it, a reflection of the universe becoming aware of itself. But could the universe always keep some secrets? It's possible. Symmetry can be broken, sometimes in ways that are fundamentally unpredictable. The quantum world is filled with tiny fluctuations, injecting a dose of randomness into even the most ordered systems. Some dimensions or fundamental symmetries might lie forever beyond the reach of our experiments, no matter how advanced they become. And even if we did uncover the ultimate mathematical equation for reality, would our minds, evolved for survival on a small planet, ever be able to truly grasp its full meaning? Perhaps, but the thrill of science isn't just in finding the final answer. It's in the exploration and piecing together the puzzle, mapping the fragments of truth we find, and standing in awe of the breathtaking patterns that emerge along the way. The coming decades promise to be a golden age of discovery. We're building colliders that will smash particles with energies unseen since the universe's first moments. We're launching space telescopes designed to map the grandest symmetries of the cosmos. And we're developing quantum computers that can simulate the complex hidden geometries that theory predicts. Each of these revolutionary tools will allow us to peel back another layer of reality, testing the idea that the universe is, at its core, a manifestation of perfect mathematical order. And this isn't just an abstract quest. Discovering new symmetries could unlock technologies we can barely dream of today: revolutionary quantum materials for near-limitless energy, new forms of propulsion by understanding dark matter, or maybe even a deeper mastery over space-time itself. Our search for symmetry isn't just about understanding the past, it's about building the future. But perfect ultimate symmetry does exist. The implications are staggering. It could mean that at the deepest level, the universe is deterministic, a story already written in the language of mathematics. But it might also show how that perfect order gives rise to the beautiful complexity and even the freedom that we experience every day. It would suggest that mathematics isn't just a tool we use to describe the universe. The universe. And our ability to even comprehend these ideas hints at a deep connection between consciousness and the cosmos, as if we are the universe's way of knowing itself. The pursuit of symmetry is a journey to the heart of the biggest questions. Why is there something rather than nothing? Why is there order instead of chaos? And can we, who are made of stardust, truly understand it all? As we trace this thread of symmetry from the tiniest particles to the vast spirals of galaxies, from the crystals under our feet to the equations in our minds, a breathtaking vision comes into focus. Reality isn't just a random series of events. It is a structure elegant, balanced, and woven together with mathematical beauty. Symmetry, both seen and unseen, is the master architect of all existence. Perhaps one day we will find that single, unifying law that explains everything. Or perhaps the horizon of symmetry is infinite, a journey without a final destination. Either way, this quest unites us all in a shared adventure, to understand the hidden order of the cosmos, and to glimpse the universe not just as it appears, but as it truly is. Thank you so much for joining us on this journey to the heart of reality. If you enjoyed this exploration, don't forget to like, subscribe, and hit that bell to be notified of our next video. We'll see you then.